in the book, he does go through a way of approximating the sharpness of the multiplicity function, i.e. the multiplicity of max. And this problem explores another way of doing so. So for part A, it says we have two identical Einstein solids with each with n oscillators, so we have a total of 2n oscillators in thermal contact with each other. Suppose that the total number of energy units in the combined system is 2n. How many different microstates are there for this combined system, i.e. how many possible values of the total energy can the first solid get? The first solid can get 0. So I'm gonna start with part A. It could get 0 units of energy. It could get 1, it could get 2, all the way up to 2n. So that means there's going to be 2n plus 1, counting the 0, different macrostates. So the answer for part A would be 2n plus 1. 2n plus 1 macrostates. Part B, it says use the result of problem 218. I will probably record a different video to prove the formula for 218 when I get around to it, but for now we're just going to use it, and we have to use that result to approximate the expression for the total number of microstates for the combined system. In other words, we are taking those two solids and we're turning them into one solid, okay, since we need all the microstates. Regardless of how the energies are divided up between both of these solids. So in our case then, in formula 218, the total number of oscillators, so I'm gonna do B here because I need the space. The total, we know that the total number of energies will be the total energy provided in the question, which is 2n. So I'm gonna replace Q with 2n in that equation, and I know that big N will now turn into 2n. Because I have n oscillators on each solid, and if I'm combining them, I'm ending up with 2n oscillators. Okay, so then I could find the multiplicity. So I'm just gonna copy the formula in the book, replacing Q with 2n and n with 2n. And so if I do that, I will get 2n plus 2n over 2n to the 2n times 2n plus 2n over 2n, and this is raised to the q, which is 2n, and we're going to divide this by, so I'd better line this up here. This is the main divider, with 2 pi q, which is now 2n, times 2n plus 2n divided by 2n divided by n, but n is now 2n. Okay, so let's go ahead and simplify this. So we will get 4n over 2n would be 2n to the 2n times 2n to the 2n divided by bracket here 4n, so I could cross these out and I would get 8 pi 2 plus 2 4 8 pi n, and here we're gonna get 2n and 2n. So 2 to the 2n times 2 to the 2n will be 2 2n to the 4n divided by 8 pi n. Okay, we're not yet. This is the answer. Should be here 2 to the 4n. So let's simplify it further. So we're gonna get oh, I forgot. Wait, I messed up here. This is divided by 4n over 2n. 2n to the 2n. Yeah. 2 to the 2n. Oh, the n cancelled, didn't it? There's no n here. I apologize. The n's cancelled, so this n cancelled. Oh, okay. So sorry about that. So we get 2 to the 4n, because here we cross these out. Okay, so we get 2 indeed 2 to the 4n divided by 8 pi n. For part C, he says the most likely macrostates for the system is the one in which the energy is shared equally between the solids, as explained clearly in the text. You would think that's, you know, it's all probabilities and that's the most probable one. When it's shared equally between the solids, use the result of problem 218 to find an approximate expression for the multiplicity of this macrostate. Okay, well, he kind of walks you through the question. So if we have the two solids and then the energy is to be shared equally between the two solids, that means let me do it here. That means the energy will be split in half between the two solids. So solid A will get the same amount of energy as solid B, which would be 2n over 2, which would be n. Okay, so then we could find the multiplicity of solid A by using the formula from problem 218, and since it's shared equally, solid A and solid B will be the same, so we could just find it for one of them. So the multiplicity that's for solid A, that's most probable. So I will go to the formula and I will just plug it in as is, since now Q is Q and N is N. Q is N, sorry, and N is N. So we will get so Q is N, so we will get N plus N. So I'm plugging into the same formula I used in part B over N. Raised to the N times N plus N over N raised to the N all over. Let's put the main divider here. 2 pi N n plus n all over n. And we will get 2n over n. This would be 2 to the n. The other one also would be 2 to the n, divided by this n would cross out, and we get 4 pi n. 4 pi n. So this would be again, both solids are equal, 2 to the 2n divided by 4 pi n square root. So this is the most probable macrostate for solids A and for solid B. Now if we want the total we would multiply these multiplicities because they're independent. So the most probable multiplicity or macrostate or the total multiplicity of the entire system made up of solid A and solid B, let's call it most probable, would be multiplicity of A times multiplicity of B, as clearly illustrated by the tables in your book when he does those examples, will be 2 to the 4n divided by, so I'm just multiplying 2 to the 2n over square root 4 pi n by itself, or squaring it, so I get 2 to the 4n over 4 pi n. This would be the answer to part C. Part D is where we put it all together in order to find out the width of the shape. So we're trying to get an idea here. So in part B, if you recall, we found out the question was asking for an approximate expression for the total number of microstates of the combined system when taken as a whole. So part B, in other words, was basically telling you the area, the total area under the entire graph. That's the and then part C, the most likely macrostate of the system. Basically that was just the most likely microstate is the peak of the graph, which would be the highest point on the graph. In other words, it would be how high the peak is. So if I use a very crude approximation where my shape is a rectangle, the area of the rectangle is height times width. The height is the answer from part C, which is the most likely microstate. Answer B is the area of all these microstates. So if I divide the area by the height, I would get the width of the peak. So we will do that for D. So D, the width of the peak will be the area divided by the height. The area was just the total number of the microstates when the whole system was taken as a whole. That would be the answer for part B, which turned out to be 2 to the 4 where is it? Yeah, 2 to the 4n over square root 8 pi, 2 to the 4n divided by 8 pi n, and we're going to divide it by the height, which is the most likely microstate. That came from part C, which is 2 to the 4n, right there in blue, divided by 4 pi n. Let's simplify this. We get Okay, so those two cancel out and I get 4 pi n divided by 8 pi n square root, and of course this could be simplified further. 8 is just 2 root 2, and we get 2 over square root of 2 is just 2 square root pi n, 2 square root pi n. So the width of the peak would turn out to be 2 pi n. Okay, and then he says, so this is how wide it is, and then out of all the macrostates, well, how many macrostates we have? It's q plus 1, right? That's all the macrostates, and then we have 2n. Q is 2n plus 1, so there's 2n plus 1 macrostates. We can approximate this to about 2n. We can ignore this one. So that means, then he asks you, out of these macrostates, what fraction have reasonably large probabilities? Okay, well, if I take my answer that I got and I divide it by this number of macrostates, I would see how many of them have a significant probability. So that means it's 2 pi n divided by what did we say? Square root 2n, right? And of course this would be square root 2 over 2. That would be pi over n to the half. This would be n to the half. There's a pi here, and then there's a 2, so this would be a 2 here, and a square root. Okay, now this so then he says to apply this to a so this fraction would have reasonably large probabilities, and then he says evaluate this numerically for the case when n equal 10 to the 23. So if we plug in 10 to the 23 here, let's see what we get. 10 to the 23, oops, sorry, pi divided by 2 times 10 to the 23, and if you plug this in, you get 3.96 times 10 to the minus 12. It's very, very, very small, which is expected, right? This is the fractional width of the peak. This is very small, and this tells you that it's highly unlikely that this system will ever be found in this state, will ever be found with any energy distribution that gives a different distribution from the most probable case, where each one of the solids has half the amount of energy. These were the answers required. Let me just box them. Okay, so putting everything together, this question was there to summarize is to figure out the area under the graph. Well, first use the equation to figure out how many different macrostates there are using the equation from problem 218, and then figure out the area under the entire graph, right? By figuring out the total number of the microstates of the combined system. Then going into the most probable case to figure out the height of the peak. That's where each one of the solids have half the amount of energy units available, that would give you the height. Knowing the area and the height, you could figure out the width of the peak, and you can see how many you could see what's the fraction that has reasonably large probabilities using this. So it's just a different approach to figure out the width of the peak from the one used in the textbook, to arrive at the same conclusion by figuring out the equation of the Gaussian distribution as derived on page 65. This concludes the problem.